I try to do mathematics and metaphysics using as a fundamental idea a measure of information, algorithmic information, which is basically the size of programs in bits. And this is my proposal, that this is a unifying idea that applies to the physical world, and it applies to analyzing what mathematical theories can achieve. So I even have a proposal that I've worked on in collaboration with Virginia Chaitin, called metabiology. We've decided to call it, because it's not a
aware of that.
Yeah, it's not a theory of, it's not a theoretical biology. It's sort of one step removed. So it's the way Virginia puts it, it's an attempt to extract the fundamental mathematical ideas from biology, and recently
to extract. To make them more visible, and to extract them, to get rid of them?
No, to make them more visible and develop them mathematically as a little mathematical model, a mathematical theory. And recently, while we were in residence at the Institute for Advanced Study, I saw how to enrich my model substantially. This is a paper that's on my website. It's called Metabiology 2.0. And I had been searching the original metabiological.
That's great,
model.
because you're working all together intellectually there, like metabiology and metamathematics.
Right. We didn't just work together. We didn't just work together to have our two delightful children. We also spent years working together on metabiology. I from the mathematical side, Virginia from the epistemological side. But anyway, the version of 12 years ago is just a single organism that is mutating, and there's no population, and there's also no geometry. It's a very simple model of a software organism, but it's not moving in space. There's no physical world, and there's no population. It's just one organism.
So what is metamathematics?
No, metabiology.
Metabiology, okay.
What I realized, it only took me 12 years, is that it's rather easy to change this to a model in which you have a world which is a plane, an infinite plane divided into identical squares, and you can have organisms, a population of organisms, software organisms, spread all over this, one in each square. So each square can contain an arbitrarily large software organism, an arbitrarily large amount of information, finite. And you also have a population of mutagens.
Large but finite.
Well, yes. Well, if you actually work on an infinite plane, you could actually have an infinite population. Right?
You could have an infinite population.
Yeah. And then you have mutagens. And so the idea in this model is, so the organisms can move one square at a time, up, down, left, or right. And so can the mutagens. And when two organisms collapse, the fitter one replaces the one that's less fit. So you end up with two organisms where you had two before, you have two again, but now they're identical and they're the fittest organism. And also when a mutagen hits an organism, abuts an organism, then you apply an arbitrary algorithmic mutation to the organism. If that gives you a fitter organism, it replaces that organism. Otherwise, the organism stays the same. So this is you can prove that this is an open-ended evolutionary system, I believe.
What do you mean open-ended?
Which it'll keep evolving forever, and the organisms will get more and more complex.
Okay.
And I just gave
So it's like Windows and Windows.
Well, I just gave a talk on this at the World Conference of Complex Systems yesterday. On this, that it was taking place in, is it Mohammedia?
Mohammedia.
Mohammedia. Yeah, I don't know I can't pronounce that too well. And there was a gentleman there who's worked in related areas, and who knows everything that's been done, recently in this area. I'm sort of out of touch. And they conjecture, there are models where people conjecture that it's open-ended evolution. The sad case is when you have an evolutionary model and it stagnates, and this happens very often when you simulate it, that for a while the organisms seem to get better and things get more interesting, and then somehow you get an organism that is so efficient that it takes over everything and then evolution stops. But people have models that they conjecture are open-ended, which means we'll keep evolving forever to more and more complex organisms.
So that means...
But I can prove it.
Yeah.
My model, I can actually prove it. And this is something that people who work in this area have not really tried to do, to prove theorems.
Okay.
So the difference with my models is they are constructed in such a way that you can prove things.
That's what is in, actually, yeah. That's what is
yeah, so I was delighted to have somebody in the audience who knows a lot about all of this and knows about the work that's, I'm sort of, I'm getting old, I'm practically retired except for the year I spent here in residence at the Institute for Advanced Studies, and I'm out of touch with a lot of the developments going on. And I was very interested to talk with someone who really understands what Virginia and I are trying to do with metabiology and who's aware of all the related work.
So in a way, I think the common ground, of metabiology and metamathematics is
that there's infinite opportunity
it's a way
grow.
To open a window
to infinite creativity.
To infinite creativity
in biology.
To what we call infinity or infinite creativity or something. So on that aspect, we could say that it's a way to starting with something that is very
simple,
very simple, so scientific and rational, to make it metaphysical. Because in fact, metaphysics is that, historically. It's just like to go beyond, every time to go beyond. That's the reason why it means after. Meta means after.
Okay.
After. It's just like, okay, but after. And it works very well with metabiology, the conception of metabiology of your wife, Virginia, and your own conception of metamathematics, because it's always like if you, after, what about after? And it becomes like
you're standing outside.
Forever after. And so we reach some kind of an understanding of infinity. There is always after. At the end we say, okay, we don't need to prove more because we have proved that there is always after, so that's infinity. And so it's
unlimited creativity in the case of biology.
But
open-ended creativity.
But what will make it really metaphysical? It's the fact that, but maybe you will tell me that's not that. The fact that by thinking those models that make you see or realize infinity with metabiology or metamathematics, you start to think that not only infinity is the development of that it's a development, but it might be the primary reality of the world. Like it's not after, but actually there will be what we call in philosophy ontology. It's what Aristotle say. It's primary philosophy, philosophie première. So what looks after, it's actually related to what is before. That is the very principle that.
Yeah, what is it that exists? What is the substance of the world?
And at the end, it's just exactly. Right. But when we thought about a substance as something that is just here and now, we actually were wrong, because the substance is infinity. And so if it is the substance, of course, you can have the conception of the substance that is like this thing that you can grab, because it's the idea that you will grab it. And so in that way, this thing that we can't grab, that is infinity itself, that you can reach by developing metabiology or metamathematics, And that make you come back to primary philosophy like ontology. It make me think. It's like if infinity was the hidden God of mathematics, a way to not talk about God but actually God itself.
Well, mathematics is a world where we talk about infinities, and in a sense, it's like medieval theology, pure mathematics, because mathematicians live in the Platonic world of ideas, of mathematical ideas, and my limited understanding is that the Platonic world of ideas doesn't have much favor with contemporary philosophers, right? But I think Gödel said, that pure mathematicians are in a sense still, at least he was still living in medieval philosophy because he believed in the Platonic world of ideas. I think hopefully human imagination is unlimited. And my hope is that we've discussed a lot of very interesting ideas. My hope is that we can't imagine the ideas that people will come up with in the next 50, in the next 100, in the next 200 or 300 years. If you extrapolate from the science and the philosophy of 50 years ago, 100 years ago, 200 years ago, 300 years, 4 or 5, the mathematics has changed radically, the physics has changed radically. I think, philosophy, there are new philosophers, but, Plato is still relevant. You don't throw away Plato, right? But my hope is that the future will have a lot of surprises and that our children and grandchildren and great-grandchildren will have a lot to do, and we'll live in a fascinating world of ideas that we can hardly imagine now. Maybe we can, with this conversation, maybe we get glimpses of the future possibilities. But I think our children, grandchildren, and great-grandchildren are going to actually develop theories and understanding of a lot of these things that we can only speculate about in our dialogue.